So this is Jen Pei from Duke University. I have the honor to chair this section. And the first speaker of this breakout section is Professor Heather Kulik from MIT. She is a pioneer material science, computational material science engineer. So please join me to welcome Professor Heather Kulik from MIT.
So it's my pleasure to have a chance to speak. I've never spoken immediately after a day of 3 Nobel laureates. So today I'm going to tell you a story from my lab as a computational chemist. And where I'm going to start is how I would have given this talk a few years ago. So my lab's been using artificial intelligence to accelerate the discovery of materials for about 10 years now. And we work specifically in a class of materials called transition metal complexes that are very complicated in terms of their electronic structure. So in order to understand them well, you need difficult quantum mechanical methods. And the talk you just heard earlier today is a really good introduction to that. But the idea is that we have these well-localized metal centers, and these give rise to really interesting and emergent properties in catalysis and sensing as molecular magnets and so on. But the challenge is that in order to design in this space, there's so many more design knobs than there are for organic molecules. There's the quantum mechanical spin of the transition metal. There's the oxidation state. There's the overall structure of the molecules. These molecules can be quite large. So my lab was interested in getting into this in the context of artificial intelligence accelerated discovery, just to be able to screen these spaces much more quickly. So one of the first things we did was back then what was quite popular, which is feature engineering, in order to be able to develop neural nets that could predict quantum mechanical properties of transition metal complexes in a matter of seconds instead of hours or days that DFT would require. This led us down the path of using them with genetic algorithms to search large spaces. We also did some work in trying to understand how could we do uncertainty quantification. And then this ultimately led to subsequent scaling up. So we could do things like now search through a space of 2.8 million redox couples, achieving at least a factor of 500 speed up over conventional random search. And one of the things we did that I'm particularly proud of is we also incorporated the fact that we were doing all this accelerated search using computational data. We actually incorporated the uncertainty of the DFT functional that we chose into those predictions to make it more robust. I'm not going to talk about that today. We extended it to catalysis, and we also started to look at metal organic frameworks. There are many other chemists in this area who've worked in artificial intelligence accelerated transition metal chemistry. But actually, the reason I'm showing all of this on one slide and that is that I'm not going to talk about any of this today. This is the kind of talk I might have given a few years ago, which is basically to say in a nutshell that artificial intelligence can really accelerate our search of space and search of materials. But typically when I gave a talk like this, I would get a number of questions. And what I'd like to do is I'd like to go over some of those questions and talk to you about what comes next. What is beyond just getting to the answer faster. And so the first question I would get is, okay, you've made all of these computational predictions with AI. What about experimental validation? And on top of that, when you do all this artificial intelligence screening, what machine learning predictions are actually surprising? And then how do you know what you've discovered is actually really new? What about real materials in the lab? What about real practical considerations? And what about the fact that if you're doing all of this with DFT, it's not accurate enough? So in about 25 minutes, I'm not going to be able to answer all of these, so I picked and chose my favorite questions, and I'm going to focus primarily on answering these first 2 questions. How do we get from a computational AI-accelerated prediction of a material's property to true experimental validation? And when do we actually have predictions from machine learning models? When have we actually been surprised by what those models have shown beyond what's typically called chemical intuition? And so in order to tell you the story that answers those two questions, I have to introduce you to a bit of an esoteric space of materials chemistry. And it's a space where trial and error experimentation is still pretty much the only way to study it, and it is extremely slow. And that is in the properties of polymer networks, and specifically in the properties of polymer networks enhanced by what are known as mechanophores. So this paper from Science in 2023 showed a kind of intuitive concept, but one that took many years of careful experimentation to prove, which is that when you create a network of polymers and you incorporate what's known as mechanophores, weak units that will break their bonds selectively, you can actually strengthen the overall property of the polymer network. And where this is advantageous is we all know plastics are a considerable problem, both for their degradation and their recyclability, but if we can make stronger polymer networks, that means that each plastic that we introduce into the world can be used more sustainably for longer before it has to be recycled or disposed of. So this is a really important idea that can help fundamentally change a number of ways that we think about manufacturing plastics. Now, along the same time, there was another observation, and this was from another lab published in Nature Chemistry in 2021. Most mechanophores are organic molecules, but it turned out that ferrocene can act as a mechanophore. Ferrocene is a transition metal complex, and it can do so in a way that's a bit unusual. So you can, depending on how you pull on the ferrocene or what its local chemistry is, you can get either a very reactive mechanophore, which is like what we'd like to incorporate into this polymer network, or a less reactive one. And so each of these insights required years and years of experimentation. We were interested to know, could we accelerate this with AI? And what we were aiming to do was identify ferrocenes that we could incorporate into polymer networks, but not doing it with the chemistry that had been accomplished to date. And the reason we were so drawn into this idea of doing this with ferrocenes is because it allowed us to sidestep a key question in AI accelerated discovery, which is of synthesizability. In particular, ferrocene has not been extensively studied as a mechanophore, but it and its derivatives have been extremely widely studied in the context of transition metal chemistry and redox chemistry. So if you go into the Cambridge Structural Database, which is a database of all known crystallized and solved structures, you have over 5,000 unique ferrocene compounds. That once we then attach polymer attachment points to them and we're going to yank on them, that leads to 12,000 possible solutions. And each one of these experiments would take months to years to just do one of these ferrocenes. So we're definitely not going to do it experimentally, but even computationally to do 12,000 DFT calculations where we are going to impart the force, the effective force on these ferrocenes, that would be very challenging as well. So what we did instead was we took an initial sample of the space of candidate ferrocene complexes, about 5% of the space, and we then trained a machine learning model to predict the difference between what we call high force compounds and low force compounds. So we used this cutoff here of 3,500 piconewtons and said, okay, for the most part, we're just recapitulating what experimentalists had observed, which is that that in order to get low force breaking, we need to have this bridge, but this bridge is incompatible with the polymer networks we're trying to design. So what we're really looking to enhance is this green tail. And so we used this trained machine learning model to then rescreen the remaining 11,800 compounds we hadn't studied. And indeed, when we then recharacterized them with these force-imparted DFT calculations, we saw a significant enrichment in this tail. So we saw many more compounds that had lower force, but were not bridged. And several of these designs were intuitive. So if you had asked the experimentalists beforehand what's going to work, they would say, oh, maybe we can put a hydrogen bond between the upper and lower parts of the cyclopentadiene, and that'll mimic a covalent bond. It'll be a weaker version of a covalent bond. And we saw things like that. We saw things like pi-pi stacking, but we also saw a number of surprises that I will tell you about in a moment. We didn't continue an active learning workflow like the one I showed you on the first slide, because after one generation, we retrained the model on all of this additional DFT data, and we did not see any predicted new compounds. Only around 100 new compounds were predicted to be low force after retraining by the model. So one of the things that I sort of skipped past is the fact that our model, in order to be low cost, was trained only on the molecular graph of the molecule. And so you might expect sterics to play a really large role in this, and indeed that's what we find. So there are other features like dihedral angle. So basically, depending on how aligned the way we pull on the molecule is, alters its force. But an interesting thing that emerged that surprised us was how sterically crowded the cyclopentadienyl ring are. So how bulky the ferrocene is really seemed to dictate reactivity. And then finally, the one that we expected. So this is the one that was a little bit surprising to us. The one we expected, the non-covalent interactions also play a large role. There are many more features that didn't correlate. But this is the one, again, that we could have predicted intuitively. We find a way to show that adding non-covalent interactions indeed lowers force. So here are two examples. One is a strong hydrogen bond, and the way to read these graphs here are, this one is the standard ferrocene. And if we see the vertical line crossing this horizontal line at a lower force, this is something called an EFEI calculation, then that suggests that this molecule will break apart at a lower force from a single molecule force spectroscopy experiment. And so what's happening is hydrogen bonding is stabilizing and making the molecule more susceptible to peeling at lower force, and so is pi-pi stacking. So these are all of the things that, again, are not too surprising, and expert chemists could have predicted that all of these would happen. So here's where the surprising thing came about. So we had also noticed that steric bulk seemed to lower force. And in particular, we pulled out this one particular example, which is identified by its CSD ref code NUSSEG. And in this one, we have a TMS group on the cyclopentadienyl ring. And the synthetic chemists came to us and they said, could you simplify it? Could you get rid of that extra carbonyl and just do the TMS? And we said, sure. And you can see that we still get the stabilization, so this is still crossing at a lower force. And we had a hypothesis about why this was working, so we analyzed this quantum mechanically. And what we found was that we were not just introducing steric bulk in a sterics kind of way, but one of the things we were doing is we were pushing electron density onto the iron. So we had preferential transition state stabilization of the iron so that it was much more comfortable with having the one ring pulled off. And so we were stabilizing the transition state. And this is something that could not have been anticipated at all prior to us carrying out these calculations. So this was truly surprising to everyone involved. And we hypothesized that the way to show that this was in fact this electronic transition state stabilization effect that had never been observed before was to move the TMS group to the ortho position, and then you wouldn't have this electron density being pushed preferentially into the iron in the transition state. And indeed, that's what we see. If we move the TMS group to the ortho position, then we're back to the original standard ferrocene. So from around 5,000 initial candidates, we selected this MTMS ferrocene and handed it off to the experimentalists to ask them to synthesize it. And so what you should expect to see based on these predictions from our simulations is you should expect to see if you put this molecule in a single strand, it should be more reactive. So it should break faster. But if you put it into a polymer network, then it should make the polymer network tougher. And so first I'm showing you the single molecule strand experiments. And so what we see is that in comparison to standard ferrocene, we have a more reactive strand when we put MTMS ferrocene in here. And these are experimental observations. But more interestingly, you actually see that the molecule incorporated into the polymer network is overall 4 times tougher than the standard polymer before we incorporate any mechanophores, and it's twice as tough as with just a standard ferrocene. And my favorite thing about this is that this is an effect you can see with your eye. So on the right, you have the polymer network with our designed molecule in it. In the middle, you have ferrocene, and on the left, you have just the polymer without any mechanophores. And so they're all going to tear, but the control has already teared. Ferrocene tears next, and our design polymer tears last. So in a matter of months, we went from 5,000 possible experiments, which would have never been done in the lifetime of any of the researchers involved. But we were able to make predictions on the scale of months with computation that we were then able to see and realize experimentally in the lab. So now I'd like to switch gears to something that you've had the timer stopped, by the way, that you've had you've had a great introduction to yesterday, and I won't argue that I can possibly hold a candle to one of the innovators of the lab, but I want to talk a little bit about real materials, and the way I'd like to talk about them is talk about metal organic frameworks. And so one of the challenges of metal organic frameworks, they're beautiful materials, but they suffer from reliability issues that limit their scaling. So there are many issues with MOFs. One is their cost to synthesize, but one of the chief challenges is just knowing if a MOF you synthesize will be stable. And so we're really interested in learning directly on literature data from MOFs because, as you've heard, the field of metal organic frameworks is a vast one that has led to thousands of researchers worldwide working on it. And so this motivated us to think about how could we leverage the thousands of experimentally characterized MOFs and the research people have done on it. And so we had developed some featurization extensions that work directly on the molecular graph, and so that allows us to learn directly on experimental observables. And we were doing this in the days when it was a lot easier to work with publishers to download large corpus of data. And so from that large corpus of data, we did two things. One, we extracted one aspect of MOFs that can limit their use, which is once you synthesize a MOF, can you remove the solvent molecules that have been co-crystallized with the MOF to make open pores for gas storage or catalysis. And that's a classification task based on the sentiment in the text itself. And then the other one that was lucky for us that people report in large numbers, and by here large numbers I mean thousands, is thermal stability. So how thermally stable is a MOF? If you heat it up, does it lose its crystallinity? And this is a huge challenge for applying MOFs in the field of catalysis, which is most of what I'll talk about today, because you start to heat up a MOF to do a reaction and the MOF loses its crystallinity, which is ultimately what has led to the limited application of MOFs, which are really attractive for catalysis in their application for catalysis. And so we were able to train pretty decent models, one that could classify and predict activation stability, and the other that could predict the thermal stability of a MOF. At what temperature would it lose its crystallinity? And interrogating the MOF predictions, the ML model predictions on MOFs, tells us why the heuristics we found in the literature would fail. In order to do this, we looked at the feature importance of what the models had learned on the roughly few thousand reports it was trained on in the literature. And one was that for activation stability, the linker, the organic part of the MOF, not the SBU, is what mattered most. And so, for instance, if we take a look at this particular MOF here, it has a low activation stability. This number in red is closer to 0 than it is to 1. It has good thermal stability, though. So our model would pick up on the fact that the methoxy group on the linker is hampering its activation stability, and in fact removing that is correctly predicted by the model to then recover activation stability. If we had focused on just simple heuristics, we might have focused on swapping out the metal, but swapping the metal would have done nothing to improve the activation stability. So heuristics focused on the metal have no effect on the property that we want to optimize. Now, thermal stability is, again, really heavily weighted towards the linker. And so optimizing the linker in a MOF is really key for increasing its thermal stability as well, but I'm coloring it here more blue because it's more of an electronically driven phenomenon. In particular, this MOF here, it's a copper MOF, and it has a thermal stability of 182 C. The average in the set that we collected was about 360 C, so this is a really low stability MOF. And so what our model does is identifies that it's important to add electron withdrawing groups to the linker, and that'll strengthen the metal linker bond. And indeed, doing that allows us to raise the thermal stability of the MOF by around 130 C. So one of my favorite things about this is that all of this is on a website where you can interact with it, and you can look at model predictions. There's other models we've developed for water stability, for gas separations. You can look at where the data comes from and where in the distribution your MOF sits with respect to the training data. You can also rate our predictions. All of our predictions are extracted from the literature. Some might be more accurate than others, and we hope in this way the models will continue to improve as more data comes available. But one of the things that I wanted to do with it was to try to look at how we could study materials for catalysis in a more compelling way. And so in particular, MOFs have a lot of promise for catalysis, but relatively few MOFs of those that have been studied have ever been studied for catalysis. So what we did was we looked at all of the MOFs that had previously been synthesized and asked ourselves, could any of them be repurposed for catalysis? And the way we did this was we looked at each MOF structure and its associated literature and threw out anything that had been studied previously for catalysis. So we were looking for things that had been studied for another reason and never before been studied. We then screened these with DFT, and we screened them for a reaction known as the direct formation of methane from methanol, methanol from methane. And the reason that we wanted to study this is this is a holy grail reaction for gas to liquid fuels. And the thing that surprised us was that all of the best MOFs that came out of the screen were manganese-containing MOFs. So if you look into the literature in the community, those who have been studying MOFs for catalysis have only really been studying iron-containing MOFs because nature uses iron. But we were pretty surprised that the energetics we were getting out of all of our manganese MOFs were easily as good as what was out there in the literature for iron MOFs. And so with Mircea Dinka, we studied one of these MOFs in more detail experimentally, and what he was able to corroborate with a combination of his experiments and our computational modeling is that these manganese MOFs are actually really good at activating oxygen and therefore have a lot of promise for the selective CH oxidation reactions, such as the direct conversion of methane to methanol. So I'd just like to finish up by telling you I told you the answers to a couple of the questions that I get asked at a lot of my talks. The first is, has anyone made anything we predict? What was truly surprising? So I showed you a space where 1 to 2 experiments were feasible per year, and we were able to use a combination of machine learning and computational chemistry to instead screen for from thousands of candidates to identify one particular candidate that led to overall increase in network toughness of a polymer network material, a phenomenon you could see with your eye in a matter of months instead of the decades that conventional experimentation would have happened. Honestly, if you ask me, we probably would have never found that material unless we had carried out this approach. And I told you a little bit about how realistic systems learning from patterns and data allow us to go beyond conventional heuristics. I didn't have a chance to talk about it today, but we've done the same thing in understanding metal ligand bonding and metal ligand hemilability. So basically, how can we learn directly from these large experimental data sets to ultimately predict beyond heuristics? There's obviously new questions to answer that I haven't answered yet that I like to think about. So there are many cases where a lot of times AI is empowered by and accelerated by quantum chemistry. But there are many molecules for which conventional electronic structure approaches still struggle, even the gold standard coupled cluster that you heard about earlier. What should the gold standard be when we're studying totally new materials for which we have no benchmark data? Can generative models provide truly exceptional novel ligand chemistries? If not, what else do we need? And now that we can have AI and ML answer scientific questions, including agentic AI? What types of scientific questions are still answered inefficiently by these approaches, but quickly answered by humans? And a question that I ask myself all the time, of course, is, what is the role of the domain scientist in all this? What is the role of the computer scientist versus the domain scientist? Obviously, I'd like to believe I still have a role, but sometimes it's sort of important to think about, what do we call intuition and what is the role in that? So I'd just like to finish by acknowledging the students who've done the work over the years. Most of the work I told you about today was done by Ilya Kevlishvili, who has his own lab now at Baylor. And then some of the work I told you about today was done by Hussein Adamji, as well as Aditya Nandi, who has his own lab now at UCLA. And thanks for your attention.
Great. Thank you very much for the wonderful talk. So we probably have time for one quick question. Yeah, please.
Hi there, thank you for this wonderful talk. Suppose that two AI scientists come to you and each one of them has a system to predict molecules. How do you test them to know which one is best?
Do you mean like a generative model, like a diffusion model?
Yeah, two generative models, and each one of them takes time to learn how to use and so on, so there is a big investment, and you've got to choose one or the other. How do you decide?
Well, so we've done this recently with transition metal complexes. We have a model that's trained on the Cambridge Structural Database to predict metal ligand coordination and hemilability, and we've been using that to validate language-based models that someone else developed for generative construction of transition metal complexes, and that's certainly a good starting point. So we assess how probable are the chemical bonding patterns that are observed from that generative model versus what is already known. And then for the ones that aren't already known, we develop DFT-based workflows to assess, does this seem thermodynamically reasonable? So that's what we've done to date. I think in any new space, there's always new challenges.
Great. Okay, thank you so much. Now we have our second speaker, Professor Jiadeng from Princeton. He is an expert in computer vision and artificial intelligence. So please join me to welcome Professor.
Good morning, everyone. I'm very excited to be here. And one topic in AI I have been very excited about in recent years is what I call procedural synthetic data. Today I'd like to tell you what it is and why we think it's promising, especially in the visual domain. So you probably have heard the phrase, the ImageNet moment. It is often invoked to mean the demonstration of a powerful recipe that consists of three main ingredients. Lots of label data used to train very large deep networks on lots and lots of GPUs. Once you have all three ingredients, as people have put it, success is guaranteed. In the literal sense, the ImageNet moment meant in 2012, the application of this recipe to the task of visual object recognition. So it's not an exaggeration to say that what we do today in AI is basically this recipe on steroid applied to many different tasks. However, I'd like to argue that this ImageNet moment has not happened to many tasks. And the main reason is the bottleneck of high-quality data. Here, it has not happened for things like 3D vision, scientific imaging, robotics, and lots of other things. So let me give you some examples on why it has not happened and why data is a big bottleneck. Take 3D vision as an example. So here is a task in 3D vision where you try to track the object pose from a video. To apply this recipe, we would need lots of label data, where you have a video coupled with accurate 3D annotations of the 3D poses of the object. Here's another example in 3D vision, where you take an input image, RGB only, and you want to generate the depth map for, that is a depth value for each pixel. So in this case, to apply this recipe, you need high quality depth values for each pixel. However, getting 3D ground truth turns out to be very difficult. Consider how you would go about this normally. You would probably want to use a depth sensor in addition to a RGB camera. However, it's well known that depth sensors are very limited. They do not work outside a certain distance, and they do not work on certain surfaces. For example, if the surface is specular or transparent, then you will not get depth values. As a result, the high-quality data, especially high-quality depth coupled with RGB images, is very, very limited. So how do we get around this data bottleneck? That's where synthetic data comes in. So synthetic data here means data generated by conventional computer graphics. In other words, you can think of using video games to train AI. We want to generate virtual worlds so that we can get high-quality ground truth automatically. So this will be quite obvious in the case of 3D vision, because we generated the virtual world, so we have all the 3D ground truth that we need. Synthetic data has been proven very effective, especially in the case of 3D vision. For example, here is a 3D reconstruction system that can reconstruct 3D structures from just an iPhone video. This is a system we developed. And this system was trained entirely on synthetic data. It has not seen a single real image in training, but it works out of the box on a real iPhone video. So here, we are insisting that we use old-fashioned graphics that's based on physics simulation. You might ask, it's already 2025, why not train on synthetic data generated by AI? Well, the reason is that here we actually want high-quality 3D ground truth. And the current AI models based on neural networks are not known to do this. Of course, there are other reasons, but I will not mention those today. Now, another question you might have about such synthetic data is that this notion of domain gap is that the generated data might not actually match real-world data in a realistic way. You might think of, maybe video games that don't look very photorealistic. Here's a kind of extreme example. So it's a popular synthetic data set that's used in computer vision called Flying Chair 3D. It looks like this, right? It's very not photorealistic. However, I would say that this is not a fundamentally it's not a fundamental technical barrier, because Hollywood has shown us how to make synthetic images arbitrarily photoreal. So it's mostly a matter of cost and effort. That said, there is a lot of limitations about existing synthetic data because they do have limited detail and realism and coverage, and the quantity is limited. They don't have all kinds of labels we want, and also they have limited accessibility in terms of getting access to the underlying 3D assets. So one approach you could take to get a lot of synthetic generated data is to take an ImageNet-like approach, where you go to the internet to download 3D assets to put in the virtual world, and people have done that, and it has been very helpful. However, fundamentally, the data through this route is limited, because creating 3D models is much harder than taking photos, and there is a limited quantity of high-quality 3D models on the internet, and they have other limitations, like limited control. So here, we'd like to take a new approach, which hopefully can give us unlimited quantity with both objects and scenes, and offers us fine-grained control. So here I'd like to show a video that introduces our approach. So there are actually audio with this video. I don't know if this can be turned on. Okay, so I'll answer to the question of addressing the bottleneck, data bottleneck in 3D vision is InfiniGen. It is a procedural generator of 3D scenes. It's not a static data set. Externally, you can think of it as a generative model where you can give it random seeds and other controls. And then you can sample from it a distribution of 3D scenes. And you can render these 3D scenes into images. What is different about it is its internal structure. It's not a neural network model. It has no neural weights inside it. So although it's for AI, but it's not an AI itself. So it is procedural, meaning that everything is generated based on mathematical rules. Everything includes shape, texture, material, lighting, arrangement of objects, and animations. There's no static 3D meshes that were downloaded from the internet. To give you an example of how something can be procedurally generated, let's say we would like to generate a tree. Right? We can write some rules to simulate the growth of a tree. We can say the tree starts with a stem with randomized branching, and depending on the branching parameters, we can get different subspecies of trees. And then we can have additional procedural systems that give the material of the bark. We can add additional systems for leaves and fruits. And so InfiniGen is based on decades of computer graphics research, in particular Blender, which is an open source system that provides a lot of primitives we use. In particular, we rely on this heavily on this system called geometry nodes. So what is it? It's essentially a visual programming language that allows you to compose a compute graph that expresses things like shape and texture. So it's like PyTorch in neural networks, where you can compose mathematical modules to specify neural network architecture. But here you are specifying mathematical functions for shapes and materials and scene arrangement. So here we introduced a transpiler that can turn any such compute graph into Python code that allows more flexibility. In InfiniGen, we have broad coverage of many things, including things in the natural world. So here's a gallery. Like we have different plants. We have underwater objects. We also have a tree system that's entirely procedural. We have a terrain system that's based on procedural noise. We have expanded the system to cover indoor scenes. Here is a gallery of samples of different types of rooms. So everything here is procedural, including each piece of furniture. And we also have a domain-specific language for users to specify particular constraints they want in the arrangement of objects in the scene. For example, you can write a little script with a few lines of code to say what you'd like a warehouse to look like. For example, you can say, I'd like the small objects to be packed densely, or I'd like the shelf to be arranged in a certain way. You can also say, well, I don't want any regularity. I just want an object to fly randomly in the room. That's also OK. And you could also place external assets into our procedural-generated scenes. And because everything is procedural, we can obtain high-quality automatic annotations. So here is a list of them that is commonly used for computer vision tasks. We can also have video and video-based annotations like point trajectories. So in InfiniGen, we have a big emphasis on using real geometry as opposed to fake geometry that's sometimes used by video games for efficiency reasons. And objects and scenes generated from the system can be easily exported to simulators like Unreal and AIAS Sim for training robots in virtual worlds. And for that particular use case, we have done additional optimization. We have introduced articulated simulation-ready assets. So here's a list of examples. So you have appliances or devices in your home that have particular articulation. And so you want these to be simulatable in a simulator so that you can use them to train robots in the virtual environment. And these assets are highly detailed, and they are guaranteed to be kinematically accurate because they are procedurally generated. And a big advantage of procedure generation is that you can have automatic, diverse variations. And each varied instance is guaranteed to be physically accurate. So you don't have to sort of manually design the articulation, the segment, the parts, as was previously done. And we have shown that these articulated simulation-ready assets are actually useful for training embodied AI in simulation. For example, we have actually trained robotic policies in simulation, use these procedural articulated assets for a bunch of skills that we'd like a robot to have. And we can show that this can actually transfer to real zero shot. So we can have a robot opening doors with the various kinds of handles. For example, we can, including a regular door and the door of a fridge. And so the InfiniGen has actually attracted a lot of interest in the robotics research community. For example, NVIDIA has published a tutorial about how to use InfiniGen assets with their AIAS Sim simulator. So one important property of InfiniGen is that it's compositional, because based on my current description, you might think that it's a huge manual effort that will never end, because we have to sort of manually develop generators for each kind of object, and this might take forever. However, this is not exactly the case because the system is actually very compositional. You might think that, okay, we'd like to, if we want to develop two generators, these are completely separate lines of work, but they're not. For example, the tree generator and bush generator and the creature generator, they actually can share a lot of subcomponents. For example, the branching growth generator can be shared by tree and bush. And if you want to develop a creature generator, it turns out that there are many low-level core utilities that can be shared. And then once you develop a rigging system for creatures, this rigging system can be reused by other existing generators. So we have this compositional structure, and the result is that we can easily get exponential growth in terms of complexity and diversity. So basically, whenever you add a new generator to InfiniGen procedural system, you are adding a new dimension of variation. So the complexity actually grows with the number of generators exponentially. If you add a new texture generator, it augments all existing generators. This is a big contrast with the static data set like ImageNet, right? If you add a new image, you're just adding a new data point. The complexity actually grows linearly with the number of data points. So another question you might have is that, okay, this is a generator of 3D scenes. You'll essentially define a data distribution, right? Ideally, we'd like this data distribution to resemble the real world. If you think of the set of images in the real world as a high-dimensional manifold, and this manifold can be actually very, very complex. How do we, do we need to get the synthetic data to resemble this distribution very closely? And that will seem very difficult. So our answer is that we believe that we just need to be somewhat close, but not too close. It's actually not quite necessary to be fully faithful to the real-world distribution. So here's an example. If you look at this image of a dragon, this dragon doesn't exist in the real world, but your visual system has no problem seeing it. Right? It means that the distribution your visual system can handle is actually a larger distribution than the real-world distribution. And so in practice, it might be sufficient to generate an envelope of the real-world distribution. And that's actually much easier engineering-wise. And in addition, because the system is procedural, so we can easily customize it for each application, depending on what kind of regularities and assumptions that you would like to make. If you want only corals, if you want corals only in water, and that's fine, you can specify that. If not, you can also make it happen. And a related question is, okay, let's say we'd like to approximate the real world, but we still like to cover the entire distribution, right, even with an envelope. But when will we cover everything in the real world? This sounds like an impossible task. Yes, it's indeed impossible because no data set or data set generator can claim to cover every single possible instance that will ever happen in the real world. But we would argue that it's actually unnecessary to do so. So one case in point is that the visual system of humans or animals, they were completely evolved in nature, right? They were not exposed to every single possible object, yet they still function robustly and they can generalize to new objects. If we transfer a human being from 100,000 years ago, we expect their visual system to function normally despite the fact that they have never seen skyscrapers or automobiles. And another important property of InfiniGen I'd like to highlight is that it's completely free and open source. So anyone can use it to generate unlimited image data, including 3D assets. It's just thousands of lines of code that you can get from GitHub, and the code is modular and customizable. And so an important implication of this is that data is now 100% controllable and transparent. So the current paradigm of the machine learning is that you just take data from most likely from somewhere else, and somebody provided it to you, and you have no control of it. You don't necessarily know what's in it, and it can be very messy. And then your main effort often is on optimizing the code of learning algorithm, right? And then you put everything inside a GPU, and out comes a model. But now, if data is completely procedural, the data is essentially code. Okay. And this has very important consequences because now data is just like code that can be optimized and customized. And it can be verified for security. You can make it adversarial to stress test systems. So hopefully, in the future, we will understand how to design and analyze data just like we understand how to design and analyze algorithms. And hopefully the process of making machine learning models from data would be more like a science than an art like it is today, because we can understand precisely what's needed and what's not needed, because now data is code. I would like to just give you some examples about this idea of the data that can be optimized and customized. So here, one thing that we can do with pursuit generation is that we can ablate the data very easily. We can ask questions like, okay, what makes synthetic data effective for particular tasks, right? In terms of generating 3D scenes, we can ask, okay, how should we place the object? Should the object be floating, or should there be gravity? What about the lighting? What about material? What about the background, and so on? We can look at these factors and understand how they affect downstream performance. And through this ablation, we can understand how to better design the data, and therefore we can have better data. So here, this is as an example, we generate some novel data using our ablation study and for some 3D vision task. And it turns out that this data can actually be a lot better than existing ones. In particular, in terms of their scaling behavior, meaning that if you control for the size of the data, it will result in better generalization performance of a trained model in the real world. So here's another example of how we can customize data to develop better models. So here, a well-known challenge for 3D vision is the handling of transparent surfaces. So for example, if you take a state-of-the-art model and give it an image of, that contains a transparent surface, the model is often confused and it doesn't know what to do. Okay? And so to target this case, we can use our procedural system to generate lots of images with transparent surfaces and with high quality ground truth, right? We can make basically everything transparent easily. We can make complex lighting to challenge the model. And it turns out by doing this, we can improve the performance of handling of transparent surfaces by quite a bit. And here's another example of using procedural synthetic data to stress test a system to understand its failure modes. So here we can take a synthetic scene, we can vary some aspect of it while keeping everything else the same. For example, we can make the object slightly bigger or smaller, we can rotate the object a bit, we can introduce occlusion, and we can change the lighting, we can swap the materials, we can introduce non-rigid deformations of different objects, and then we can test the leading models. And then we can sort of discover interesting failure cases that wouldn't be otherwise apparent. For example, one of the things that we discovered is that existing models are very fragile in terms of occlusion. If you put an object inside a cage, and depending on sort of the density of the cage, they would actually give you very different predictions. That shows that there's some kind of failure in terms of being robust to occlusion. Now, what about AI for science? It turns out that there's a lot we can do with synthetic data, especially procedural synthetic data, in the context of AI for science. So I actually have an ongoing collaboration with Professor Adam Maylouf at Princeton, who is a professor of geosciences. So what their group is interested in is to understand the early history of Earth. So the way they do it is to take rock samples and sort of grind the samples down and take many photos of the cross-sections of a rock sample. And then they'd like to understand what objects are actually embedded in a rock. So there could be fossils and be crystals. And so they want to segment out these objects meticulously so to count what the different types of objects. And it turns out that existing off-the-shelf models don't do this very well, including the latest VLMs, because this is a task that requires very high precision. But if you want to fine-tune any model, you don't really have a lot of data because it's very, very costly to have experts manually trace the segments of the objects. Okay? So this is where procedural synthetic data can come in. So we're actually working on developing procedural generators for rock formation so that we can simulate the process of forming rock samples. So we would have different kind of objects like corals and like animal-shaped objects, and we would sprinkle them in some matrix, right? Of the rock, and then we can simulate what the cross-section would look like. Because everything is procedurally simulated, we can automatically obtain very high-quality ground truth, and we can use them to pre-train or fine-tune existing segmentation models. There are actually many other opportunities with procedural simulation. For example, if we'd like robots to be able to work in chemistry or biology lab, right, we'd like them to understand what's going on in terms of different objects and how they are moving. We'd also want them to be able to handle different objects, and then we can, so procedural simulation provides an opportunity to create a virtual versions, right, of such labs for us to train robots, especially in terms of their visual perception and manipulation skills. And also there are lots of scientific and medical images which lack accurate, high-quality annotations. And because often we understand the underlying formation mechanism of these images, we could probably produce reasonably faithful simulations and their ground truth annotations through procedural simulation. With that, I'd like to end my talk, and thank you for your attention.
Thank you very much for the talk. So for the interest of time, we probably will skip the question and answers, but I encourage you to interact with Professor Deng during the lunch break. Okay, so thank you so much. So now we have the third speaker in this section, Professor Jiantao Jiao from UC Berkeley. And he is also a director of NVIDIA. So he will provide us his perspective into the current AI trend. Thank you.
Thanks, everyone. Good morning. Super excited and honored to be here. So here the title is very ambitious title. Definitely we do not aim to answer all the questions here. I would like to mostly use this opportunity to ask questions, stimulate discussions, and encourage collaborations. So ASI currently is a very hot topic in Silicon Valley. This talk we try to make it concrete. What exactly do we mean by ASI? How do we achieve that? First of all, let's try to understand what we are heading towards. What is artificial superintelligence? So let's start by first defining what intelligence is by specifying what it needs to do. The punchline we want to hit here, which currently also has been observed by many people in the community, is ASI requires competency in broad settings. So there are two key aspects, competency and broadness. Let's try to motivate this from daily examples. So we like to use a framework proposed by Morris et al. In 2024, talking about different types of tasks we work on and the capabilities of AI systems. There are precisely two scopes, two axes. One is in terms of scope. We go from narrowly scoped tasks to widely scoped tasks, and from the capability level, from really bad at this to be mind-blowing. Let's try to be a little bit specific. What exactly are those narrowly scoped tasks? So basic AI, even a calculator, can do basic arithmetics. They can help set reminders on the phone, maybe maintaining calendars, summarizing a single document. Later, with this deep learning, we can actually work on more harder tasks like image captioning, keyword retrieval, so on and so forth. Recently, code completion. There are also like more ambitious, widely scoped tasks. For example, as a company, as a startup, you want to launch a product. How do you conduct a long-range project planning? You are in a very complex business negotiation. You need to understand markets. You need to understand governance. So in terms of software engineering, you are no longer really satisfied with completing like one file in your code repo. You are considering autonomous software engineering. in terms of scientific discovery, which is also a really important topic in this conference. We need to figure out how to generate a very meaningful hypothesis, how to filter through the hypothesis, how to design experiments. There are also other more complex settings, like crisis management, generating, evaluating new policy proposals, which are going to impact billions of people in the world. So basically, that's a different set of tasks. We also want to talk about the capability level. Maybe at the beginning, the AI would be quite weak. It can only handle fixed rule-based responses, very brittle. It's going to break outside the trained context, no learning or adaptation. Later, AI becomes smarter, can do simple perception and recall, or perform certain fraction of people. Later becomes even smarter, would like to get pretty well with high-level instructions, really without a ton of detailed guidance on domain-heavy tasks. And those tasks generally would require very heavy abstract reasoning, but they would likely fail without some help. And later becomes even smarter. They can do very well with abstract reasoning, independent exploration, or performs 99% of humans. And finally, it's going to really exceed all of us. So now the key aspect will be that we put existing AI systems in a chart and figure out where we are. So there will be basic rule-based systems started many, many years ago. And with specialized deep learning systems, we're able to design sentiment classifier, toxicity detectors. Later, with amazing paradigms like reinforcement learning and different domain-specific knowledge, we achieved tremendous progress in terms of scientific discovery, solving games, and produced AlphaFold, AlphaGo, Stockfish, AlphaZero, etc. And there's also another direction where we actually both scaling the level of capability and actually also the scope. For example, with OpenAI DaVinci, the GPT-3 model, we go to GPT 3.5 at the time ChatGPT was released. And recently, we do have the latest models coming from multiple vendors, OpenAI, Anthropic, Google, which really demonstrates a very fast improving level of intelligence. So one claim we want to make is that seems based on the existing evidence and the progress by the community, ASI is towards that way precisely showing that it's able to scale both the scope and actual capability all at the same time. So we do really want to motivate this because we have already achieved tremendous progress with specific deep learning systems like AlphaGo, AlphaZero, but it's tremendously difficult to take a specific design system, for example, AlphaZero, designed for solving games, and try to use it to achieve a similar level of performance like GPT-5 Pro. So basically what has shown success is better that both skill generalization and competency all at the same time. Then the key question is that how do we even do this? We have seen some promise, somehow things are moving toward the right direction. What exactly is next? So one punchline I want to hit in this presentation is that we want to scale generalization and scope at the same time by curating broad tasks and verifying them. So precisely, there will be two pillars. One is broadness, one is verification. Let's also try to motivate this. So precisely, I want to emphasize two challenges ahead, which currently really show themselves as key bottlenecks of scaling current AI's capabilities. I also believe that it really requires the community collaboration to tackle those very challenging problems. There will be a problem of scaling horizontally, which means that you are really supposed to tackle so many different tasks all at once. You are supposed to curate so many different tasks, and at the same time, you need to curate very difficult questions because the intelligence of the system are already hitting a certain level so that the simple questions wouldn't be able to enhance intelligence anymore. From a second perspective, it will be scaling vertically, which means that given that I'm dealing with a specific application with a very smart model, how do I really make sure that eventually it's going to support human? So one key aspect here I want to emphasize is verification, which I will also motivate later. The key idea is that we need to really make the AI learn as a very following the way that really smart people learn. For example, when really smart people learn, generally there may not be really very specific answers. People need to figure out their own solutions. They propose many different solutions. They get feedback. Sometimes feedback is vague, but they are able to figure out what exactly is the next proposal. So they are able to improve intelligence. So this actually requires a very strong mechanism of verification and very high fidelity of verification, which I will also detail later. So first of all, I want to emphasize the aspect of scaling vertically. Precisely, we want to achieve ASI with respect to so many different tasks in wide scopes at the same time. So we need the intelligence in terms of solving those tasks to enhance at a very rapid pace. One key aspect that has really emerged as a key paradigm is sort of verifiability. Sometimes it's even called a verifier's law, showing that maybe the real limitation of any AI progress is based on level abstract verification. Here I'm showing a particular example of verification, which is one of the simplest ones used in literature. Say you have this chemistry question, then maybe the students would be able to propose many different answers. Then the teacher will be able to tell the students which answer is correct, which answer is incorrect. Then hopefully the student can figure out the learning mechanism. So next time when actually proposing a answer, the answer is actually correct. So it's a basic paradigm. And generally, suppose you do have a system that's able to verify the answers proposed by students. Currently, we do have a certain paradigm called reinforcement learning with verifiable rewards that's able to continuously enhance the intelligence of the system. It works in the following way. So first of all, you have the training data. Here I call the SI. They will be the prompts. You can think of this as the tasks I give to the AI. So AI accepts the task. Then the policy is basically intelligence. The policy is supposed to figure out the answers. But initially, it really may not be able to figure out the right answer, so generates many different answers. That's what I wrote on the right, intelligence attempts. I'm going to attempt so many different things. Then it's going to send in to this verification module, producing a verifiable reward. So the module would be able to tell if the intelligence attempt is right or wrong. And after doing that, ideally, we should also figure out a mechanism to digest the feedback so that the next time when the policy or the intelligence proposes a new answer, the answer is of higher quality. Eventually, hopefully, it can surpass the quality produced by any human being. Based on the existing research and community efforts, it has been very clear that this part, this verification component, appears to be a very big bottleneck in current AIAS development. So I want to elaborate on this point. So the key aspect of thinking about verification is actually to think about how verification is connected to many tasks we have on our mind, in particular in terms of achieving ASI. So there are many things we want to, many tasks we want to solve, many verification we need to do, but they are kind of different. For example, I'm listing a couple of examples being talked about all the time in the community. For example, in solving Sudoku. Sudoku is one interesting example where it's very hard to come up with a solution. We need to try many times, but it's actually very easy to verify. I try an answer, I know immediately if it's right or wrong. Competition math is quite interesting because it's generally very hard to figure out the answer. But if you present your answer in natural language format, it's also very hard for people to verify. We're going to check really carefully to figure out if it's right or wrong. There's another approach, which is formalized math, such as writing math proofs using Lean. That actually would simplify the process. So there's nuances in this aspect. In terms of competitive coding, it's also very challenging because the question is very hard. Maybe it's super difficult for a person to come up with an answer. And sometimes it's actually easy to verify because we have already prepared lots of unit tests to figure out if finally the code you generate is correct or wrong. The fourth one is also an interesting one. It's somehow one example on the opposite side, because kind of it's easy to produce an essay filled with some statements, but generally it's super hard to verify every fact stated in the essay. Maybe we'll go to the library, we'll search online to really figure out what actually is going on. And the fourth one, and the fifth one actually is even related to scientific research, which is also a core topic here. How can we really figure out a novel scientific hypothesis? We have a hypothesis. How do we really verify if it's true or not? How do we falsify them? Maybe it's going to even require a wet lab experimentation. So generally, what has been observed in the community is that we are able to make very fast progress when verification has the following properties. First of all, it's precise and objective. Secondly, it's very fast because AI needs to consume lots of compute on GPUs. So we actually need to try lots of attempts all at the same time. It's also related to scalability because ideally for really challenging tasks, what I want to do is that I want to make like 1 billion attempts and maybe let the verification system tell me if I have made progress or not. And the fourth one is also extremely important in terms of providing richer signal because when you think about very complicated scientific research, we write a paper, the paper is 200 pages long, then generally the feedback provided to the paper is really not 0 and 1. It's really very detailed comments on different paragraphs telling the people how to get a better version of the paper for the next iteration. So that's exactly the challenges here. And generally, those requirements hold for both easy and very difficult environments. If it's very easy to have verification system satisfying these requirements, it will be nicer. It actually enables faster AI progress. Otherwise, it's going to encounter some challenges. Later, I'll also try to talk about what are the attempts that people have made recently to reduce the difficulty of building verification. But these are really the basic requirements we actually need to satisfy. So precisely, or more broadly speaking, for simpler tasks, very narrowly scoped, verification is kind of easy. We are currently able to verify answers for tasks that generally fall here, with some exceptions. And generally, when we move towards the widely scoped tasks, verification becomes harder and harder. So we also need to figure out a way to do this. And recently, community has figured out some initial attempts to address this problem. So to emphasize, we really need to solve verifiability for open-ended, difficult tasks for the next phase of marching towards artificial superintelligence. So one thing I want to really emphasize is that we have really built new systems of enhancing verification accuracy. And to do that, the main motivation was that it really appears verification on complex tasks is actually very challenging, and the basic method of checking won't work too well. The real reason was that the feedback to the intelligence must be of very high quality, which means that generally you really should have very few false positives or false negatives. I really would like to motivate this point through one example, which has come up again in the community where we're actually training models. So say here's a physics question. I ask a question, when object's moving, then I ask you what's the magnitude of the force. Maybe the textbook has written an answer, it's 10 newtons. But in reality, lots of other answers are actually also correct. Maybe the AI is very smart. AI figured out another form of the answers. But if the verification system is very dumb, the system was not able to figure out these actually are equivalent, then we'll be sending really wrong signals to the AI, and clearly it's going to destroy the intelligence of AI. So this point has been exactly observed in the community. For example, here what I'm showing is basically the AI system performance on the data set called the GPQA, which is the short for Google Proof Question Answering, important benchmark in LLMs. So suppose you are using a simple verification, which is stream matching, to check the quality of GPQA. You'll be able to see that, in fact, after you have run reinforcement learning on this, the quality of the AI actually degrades because you are not able to provide the verification system has very few false positives and also false negatives. And generally, the paradigm that the community has kind of figured out recently, and we're all marching towards scaling this up, is really to use other intelligences to help judge the quality of the outputs. Because generally, to enhance the intelligence of one system, you also need a really intelligent system to help judge the work. So here, it has many names in literature. Initial as a judge. Initial, it means something very narrow. Now it's much broader, also called universal reward models. And this is one attempt recently. So basically, suppose you use a universal reward model to really judge the quality of the output, to try to reduce false positive and false negative. Here, you already see that the quality improves compared to the original baseline, 29.3. And the important thing is that on many different benchmarks, or even on benchmarks where the basic stream matching approach is able to improve the quality of the system, if you finally later also adopt a new verification system that is based on higher level intelligence, turns out the performance gets even better. So that's the part of vertical scaling. I also want to touch a little bit on horizontal scaling. How do we really scale horizontally? So that's also related to the general belief we have, is that as humans, we are really exposed to many different tasks, in particular very challenging tasks that requires really abstract reasoning in open domains. So generally, if the AI has really not seen anything like this, it's very unlikely the AI would behave as a super intelligent person in terms of these very openly ended questions. So basically, we want to curate tasks to use during training across the spectrum, and we have to train it both under simple narrow tasks, such as adding numbers. We want the AI to be reliable in terms of doing that. But we also want to add in lots of widely scoped tasks, which are really challenging, requires lots of attempts, requires very rich feedback. Hopefully, AI at the same time would also be able to excel at these tasks. So there will be lots of tasks we are tackling at this time, which actually, by the way, also give rise to lots of rising companies who actually provide data services recently. So we need some form of human curated, templated, and also at the same time synthetically generated data. It really appears that each different types of data, they provide some unique value. There will be many different tasks we are already focusing on, many different types of questions we are already collecting, and it's really not enough. So generally, as a community, we really need more curation efforts, scaling the tasks and prompts we can curate. And there are actually also many different challenges related to this. One of the key reasons why certain progress has been quite slow in different domains is actually related to what we talk about in this slide. So we have been observing very rapid progress in certain areas like computation math or some basic scientific knowledge. That's really because we have already collected so much data and built very reliable verification systems that allows us to pull many attempts from the intelligence and very efficiently verify the answers produced by the intelligence. But there are many other very difficult tasks in real life, for example, related to what we do in large enterprises, the white-collar job, and some of the blue-collar job, and like scientists doing scientific discovery and doing scientific experiments. We really do not have that much data. For example, just think about understanding the domain-specific knowledge, internal knowledge of a big company, of conducting certain operations. We really haven't curated those data for AI to know, and AI is not able to get enough feedback. Very similarly, in terms of running scientific experiments, many times AI really hasn't seen how we are really conducting those experiments, and it actually also appears to be very challenging for AI to actually match similar level of performance as humans. So this slide summarizes what we have been discussing. Generally, to march towards artificial superintelligence, there are two directions we need to pay attention to. One direction is this vertical scaling. We really want to make sure we produce super reliable, highly intelligent AI that's able to solve specific tasks. There's a very high level of intelligence. We should be able to do this using a highly complex, deterministic, and universal verifiers. At the same time, we also need to significantly enhance the data curation efforts using both synthetic and data and human efforts towards the harder questions, and with the main principle of replicating the learning process of really intelligent human beings. So precisely to unlock this, we need universal, reliable, scalable, and fast verifiability. At the same time, we also need to be able to access complex, open-ended, very difficult tasks. This is definitely not something one company can do. So solving this, I believe it requires the entire community working together, and then hopefully we'll be marching closer to the goal of ASI. Hopefully, with the getting closer to ASI at the same time, it can really help us significantly accelerate the scientific discovery, which is also the theme of this conference, at the same time benefit everyone in the community. Thank you.
Great. Thank you for the great talk. So we are open for questions. Any questions? Yeah, please.
All right. Thank you very much for the talk. So I have a question about, like, what do you view as the prospects for generalizing from things that we can verify rewards for or scoring for to things that we can't? Because it seems to me like there are a lot of really important domains where the prospect for getting those sorts of verified scalable rewards is pretty questionable. So for example, developmental biology, like if you want to make a model that predicts the effects of some gene mutation on human developmental biology over an entire growing up period, that seems very difficult to get ground truth data on at scale, especially for like novel gene alterations. So if we enter into the world you're describing where we have tons and tons of these verified tasks and their rewards, where does this really get us in terms of the like really, really hard problems that data is just like incredibly hard to obtain for? Thank you.
Thank you. Thank you. I think this is a super interesting question. Lots of people are thinking very hard about this. Maybe I want to mention some of the attempts already made by community to address that. One thing might be that there indeed might be some limitations of current approaches. There could be certain settings where it's just super hard to conduct any experiment to figure out what the right answer might be given a particular scientific hypothesis. But one direction we have seen that has demonstrated the promise is actually to try to rely on the generalizability of AI systems. Somehow, one thing we observed is that suppose you are able to curate very large, diverse set of tasks with very high quality of verification systems, and you build a very strong verifier, which is a universal verifier, not exactly rule-based system. Then you ask the verifier to check the quality of certain widely scoped tasks with some seeding data. What's being observed there is that generally it's able to generalize to quite a few like new answers that generally would require lots of human supervision. Then the AIAS answer, AIAS verification, AIAS comments generally prove to be of very high quality. So somehow maybe there's this trade-off. There will be things we can verify super well. There will be things like super hard to verify. Maybe essentially it's impossible, but there will be a middle range. So what is currently showing promise is that somehow based on new training methodology, new algorithms, new data curation, we're able to move the needle towards the tasks that's kind of like very hard to verify. But maybe there's still a limitation. So that actually also means that maybe human scientists, the scientific discovery are still very much necessary.
Thank you. Fantastic talk. Just had a kind of couple of quick questions. One, you had the example of the AI being able to book your airline ticket or pick your stocks, but both cases that's kind of demand driven, and it's based on the algorithms, how many and how much demand for the stock. So more demand, it goes up. So it's kind of a moving target. So I'm just wondering how the AI product will react to that, and so that you would make money in stock or get the airline ticket at the lowest price. And then the second question is, as we move to AGI, what guardrails are going to be to make sure that AGI doesn't fall into nefarious hands and become an potentially extinction event, which has been talked about in other conferences and forums. Thank you.
Thank you. Thank you. So both are very challenging questions. I think in terms of first one, for example, stock market prediction, maybe the right way to formulate this in this presentation is think about the specific task you have scoped for AI, because there are already people doing the task. People in big hedge funds, people in independent proprietary shops trying to beat the markets. The key point is that AI should be able to replicate what people are doing. If there are certain limitations in terms of the information people can access, then maybe AI also has the same limitation. But the key thing is that can it demonstrate a certain level of intelligence to be able to replicate or even help enhance the human's behavior performance so significantly. For the second one, clearly that's a question that so many people in the world are thinking very hard about. That's also related to some interesting research question. For example, you want AI to follow specific rules. There's a study regarding whether it's even doable, because maybe if the AI system is even released, there's no provable way of controlling AI's behavior. And then there are other approaches to say that maybe under certain assumptions, we can develop a new methodology so that the AI would definitely adhere to your instructions very precisely. So that's also a very important aspect I think lots of people in the community are doing research on.
Thank you.
Thank you.
Can I question here? Thank you for the great talk. So actually following up on that particular question, could you elaborate on verifiable rewards for AI agentic systems, right? So as we move to multi-systems with multiple agents performing a task, can you elaborate in how to think about like verifiable rewards for a full AI agentic system? And following up to that question, how do you think about verifiable rewards and traceability of the actions that each of the agents in the system performs?
Sorry, I want to make sure the second part is
the second part is verifiable rewards and traceability, like basically understanding the steps that each of the agents perform in elaborating a particular task.
Thank you. Yeah. This is also a really interesting question. So maybe I can summarize a little bit what the community has observed recently. So in the very early days of the working on agentic systems, then one verifiable reward will be the final task outcome. For example, you specify the outcome, and then you let the agentic system operate in its own way. Finally, you judge whether it has succeeded or has failed. This has actually proved to be very useful for simple tasks. Very recently, there is also another trend showing up that maybe only providing the final feedback in terms of success or failure is very difficult because there has been lots of intermediate steps. Mm-hmm. There are certain actions taken by the AI is actually good. Certain actions actually not very good. You need to be able to provide very rich feedback. So that's really the recent trend. It's actually also something I talk about in this presentation. You really need to have a system so that you're able to give very detailed comments for every specific action the AI has taken, perhaps also multiple AI agents. And you also, at the same time, need to figure out the updating mechanism. After I give the AI really detailed feedback, how can I guarantee for the next attempt by the AI is able to improve? So there are certain methods that demonstrate the interesting early promising results in this direction, but it's definitely also something everybody needs to work harder on.
Thank you.
Okay, great. For the interest of time, let's wrap up the section here, but we are encouraged to get more interaction during the lunch. So please join me to thank Gentile as well as the other two speakers in the section. Thank you for your participation.